Hello there, this is Kevin from Gatsby Unit at University College London. I'm very excited to talk to you today about our work on a high-dimensional convergence theorem for use statistics with applications to kernel-based testing. This is joint work with my collaborators Xing, Andrew, and Axel from Imperial College London. The object of interest in this work is a degree 2 use statistics taking in IID data x1 to xn living in some high-dimensional data space RD. What we usually use use statistics for is to estimate this kind of expectation, and here in particular is a symmetric function u taking in two independent data points. This use statistic proposed by Hoofding gives an unbiased estimator for this quantity. And an intuition is that this gives you some empirical measurement of average distance within a cluster of IID data points handed to us. Even though this was proposed a really long time ago, this still sees a lot of important applications in modern machine learning and statistics. So needless to say, this plays an important role in distribution tests, but the theory we are going to develop in this work is sufficiently general that it applies potentially to other applications as well. When we use statistics in all these applications, a very important property we care about is the asymptotic distribution. If we know how to characterize the asymptotic distribution, we have a way to quantify the confidence interval for the statistic, and we will have a way to say what the type 1 error may be or to give power control under the alternative. So let's review the classical results for asymptotic distributions. And by this, I mean the case when dimension d is fixed and when number of examples n is large. Most of you probably know that this depends on the notion of degeneracy, i.e. whether the variance of this particular conditional expectation is zero. A non-degenerate use statistic would have a Gaussian limit, scaling with variance scaling as this sigma conditional, and a degenerate one would converge to an infinite sum of weighted and shifted chi-squares, and the variance is going to scale like the variance of the entire u x1, x2. However, what we care a lot about in modern settings is a high-dimensional setup, where dimension d is allowed to be large. There are a lot of existing results that try to study the non-degenerate use statistics in this setup, and they focus on deriving a Gaussian limit. This sounds natural because this is, after all, the limit that the classical result suggests. However, our paper is going to argue the opposite. We're going to say that the distribution turns out not depend on the degeneracy in the classical sense, but it's going to depend on the moment ratio rho d, which is exactly the ratio of these two variants that we have defined above. We managed to show that a phase transition of the limiting distribution would happen as rho d varies. So when rho d is asymptotically smaller than square root n, sure, we are still going to have the non-degenerate Gaussian limit. But if rho d is asymptotically greater than square root n, even if you have a non-degenerate use statistic, you may still have a degenerate limit. And in the intermediate regime, obviously, you're going to have a combination of both. Our paper provides finite example bounds for all of these cases described above, and in particular, we have dimension-independent bounds under a very mild assumption. The only assumption we require for the result is that u xi xj admits the following decomposition, and this decomposition is only required to hold in L nu with respect to a data measure of xi and xj for some nu greater than 2. Note in particular that this kind of decomposition is also used in proving the degenerate version of classical use statistic asymptotic distributions, and there they use the decomposition for L2. In that case, this holds without having to assume anything. Our results are therefore significantly more general than previous results. And a very surprising consequence, as I mentioned, is that a non-degenerate use statistic may actually have a non-Gaussian limit. We then look at the applications of our result to KSD and MMD, two popular kernel-based distribution test choices. We have derived sufficient conditions under which the result holds for KSD and MMD, and we also focus on a very simple setup of Gaussian mean shift to observe very interesting behaviors due to the result. We show that The moment ratio rho d that plays a very important role in the distribution depends on the size of signal and kernel bandwidth choices. And in particular, this is related to the work by Reynolds et al. In 2015, where they study empirically the behavior of test power for MMD under Gaussian mean shift. And they've observed that a phase transition of this test power would happen as your kernel bandwidth varies. Our results suggest that this is because the size of rho d is different as kernel bandwidth varies, and it causes your U statistic to have different asymptotic distributions. If you are interested in this work, or if you want to find out about any follow-up work we are doing, you are very welcome to contact me at the email address listed here. Thank you very much for listening.